So what I want to do now is I want to talk about simple harmonic motion and kinetic energy. We've already kind of explored other forms of energy. We've talked about motion and simple harmonic motion. What I want to do is I want to apply what I know about simple harmonic motion to kinetic energy. Well, the problem with that is that for the equation for velocity, we're left with this. And the problem with that, I mean, it's not really a big issue. The problem with that is that I'm going to be measuring energy as we respect with time. And we like to think of energy as time independent. We like to say, we don't want to tie time to energy right away. I mean, we can do it. We can. I mean, when we look at power, we're tying rates with energy, but for this, we don't want to necessarily do that. So what I want to do is I want to come up with an equation that's going to give me the kinetic energy at a given point instead of at a given time. So I'm going to have to do some substitution. So when we derive the kinetic energy, or when we derive the velocity equation, we came up with this. Okay. We came up with that idea. Well, I can do this. Okay. So what I'm going to do with that is I'm splitting it up to a point where this turns out to be my maximum velocity. And this is some other velocity. Well, that's all fine and dandy, and it's looking pretty good. But what I really want to do is introduce some positions. I've got a positional value here, so this time is going to go away. But I got this phi floating around, this phase shift, and phase shifts are actually kind of difficult to measure. So what I want to do is I want to say I don't want this, I want something else. I want position. So it turns out that this relationship here is going to work out to be negative x omega. I'm shifting my cosine to a sine, and that's going to give me not an amplitude. I'm talking about a given position at that point. So I'm just going to go with this negative x omega. So this term all will break down into this term. Okay? So at that point, I get the velocity at a given point is equal to this Vmax value, which is where this value turns out to be 1, which is going to be a omega minus x omega. Okay? Well, I can do a couple of things moving around. I can move that omega out, and I'm left with a minus x. And then I can do a substitution. I can plug that right into my kinetic energy equation. And at that point, I get 1/2 the mass times omega. And I'm forgetting to square. Okay? So that's the kinetic energy at a point x. So anywhere there's a point x, it's the kinetic energy. As you can see, when we reach the amplitude, the whole thing turns to 0. So that's really good for us. When this turns into 0, when my position is x, my stretch is 0, then this all turns into the maximum kinetic energy. So it seems like it's going to work for what we need it to do. So that's basically the kinetic energy equation for simple harmonic motion. Now, the potential energy equation, especially for a spring, isn't going to change. There's nothing special about the potential energy equation for a spring. We don't really need to alter it. I mean, it's an object that gives us simple harmonic motion, so we just leave it as that. Or in the case of a pendulum, which also can perform simple harmonic motion, we just leave it as this. we don't really need to make any major alterations on it. But we're going to keep with this for a kinetic equation for simple harmonic motion. Now, the other really cool thing about this is that you get this relationship. V squared is equal to omega squared a minus x squared. Cool? Well, that means that v, the velocity of an object, is equal to plus or minus omega a minus x. So it's kind of a shortcut if you're trying to determine the velocity in a simple harmonic motion. Now, we are taking a square root, so that's why it's the plus or minus values. Okay? So this is the kinematic equations for simple harmonic motion. Or not the kinematic equations, the kinetic energy equation for simple harmonic motion.